All right, so this is a power sensor. So I did a video once on a power sensor that I purchased, and I was not pleased at all with it. First of all, the board was designed wrong, and didn't have 50 ohm load on it. I don't know how that measures power. And this one seems to be better. So we'll take a closer look at it. This one's good. It's supposed to be good from 1 to 8,000 megahertz. Has a gain of minus 25 dBm, minus 25 millivolts per dB. Okay, I don't know what that quite means. And there's power ground and out. It looks almost the same, but I believe this one has a resistor. Let's see. I think, yeah, this one has a 51 ohm resistor on the input, so it's a correct power meter. It has a well, here, let me draw a picture of it. So the power meters that I'm familiar with, is that kind of crooked to the camera? There we go. The power meters that I'm familiar with, there's a 50 ohm load, right? And then you're measuring the voltage across that 50 ohm. And you generally do that with a diode detector or a thermistor or a thermocouple or whatever. But you basically have this circuit. These are the ones that I'm familiar with, right? That's a classic diode detection circuit. And when I worked at WaveTech, ours was fancier. Ours looked like this. Okay, so there was a plus and minus. So we gathered both edges, and then we measured the delta voltage across these two. So ours had a better dynamic range because we were getting double the voltage, and it was all symmetric. So it was really, really nice. And then we chopper stabilized it. So what we did was we measured the voltage this way, and then we measured the voltage this way. We swapped the two. We measure it here, we measure it here, we measure it here, we measure it here, and that would eliminate a bunch of thermal noise and stuff. And so this circuit here comes in, and the first thing is a 51 ohm resistor, and the rest of the circuit probably loads that down to 50 ohms. So but the way that they do it is they have it's capacitively coupled in to some type of detector, and this chip, let's see, what's the part number on the chip? Oh gosh, I can barely read that. All right, so the part numbers I read are an 8318. And that sounds familiar, 8318. And it says A, C, P, Z, number 10, number 1201, and then 72, a lot of numbers on this thing, 72, 5, 6, okay, whatever that is. I think it's an AD8318 power, logarithmic power detector. So instead of referencing this this to ground, so they have a differential circuit here as well. And so they're actually going to measure a delta voltage, which is really, really nice. Instead of being ground reference, they're actually going to measure a delta voltage. And what they do is they actually bring that over to here. And so they measure directly across that resistor. And they don't tie this to ground. They tie it to some node on the layout of the front end. Now, on these detectors that I used to work with way back in the day, they were good, up to 40 gigahertz and stuff, so you had to be very, very careful. So you had a connector coming in. So let's say you were building an SMA version. So you had a pin, and you had a dielectric, and then you had an outside conductor. Okay, so you had this coax, right? So you had this coax. And then that would go onto the PC board. And the PC board would look something like this. So this is a super tiny thing. Okay, but under the microscope it would look something like this. And these would somehow, the traces of these things were impedance controlled, so that you know, this is a solid. These are solid traces, and so the impedance was matched perfectly as you fed this thing in, and it would be absolutely flat SWR, or return loss and stuff. So a lot of effort was gone into making sure these were perfect. And then there was a chip, you know, a 50 ohm resistor here, right? And then that went off to ground. So this was all ground. And then across here was a zero bias Schottky diode. And then over here was a capacitor. Okay, so this is a cap C. This is a diode D. This is a diode D, and then there was a cap here C. And then they were also referenced then to an electrical ground. Okay, so there was an electrical ground here, right? And then these diodes then, let's see, did I draw that right? No, I didn't draw that right. I did not draw that right. 50 ohms. Yeah, this isn't connected. I'm sorry, this is not connected. So yeah, these weren't connected. I'm sorry, messed this drawing up. These actually went. This actually went to this ground over here, and then this little diode circuit had the voltage on it, and then that went out. That went out here, out like this, and then there was like a plus V and a minus V, and then a ground and a ground, and ground here. Anyway, it worked that way. I think you get the idea. It was very, very symmetric and all really, really smooth lines and controlled impedances. And these were diodes that you can't buy. They were special from the factory. We got first pick at them. They were very, very unusual. Maybe once a month they got to be able to build something like this. They were very unusual diodes. And anyway, that's what it takes to do a really, really good power meter. But I like the idea here that they've actually split it, and it's a plus minus, and they're measuring the voltage across that capacitor, and across the resistor, the 20. And so let's go ahead and hook this up. I'll put some pins on it so we can make electrical contact to it and see if it tracks power. One of the things I was not pleased about last time was the frequency response. Very small changes in frequency. There was huge changes in power output, which would rely on really, really large calibration problems. And from 1 to 8 gigahertz, 1 to 8 gigahertz, you would think you wouldn't really need much calibration. It would be pretty flat on that side. That's small of a range. But yeah, let's give this a try. All right, so here's the data sheet for the AD8318, 8318. And so it's got a differential input, and it has detectors along the way. So it has detectors on logarithmic boundaries, and then it has a temperature sensor to balance things out versus temperature, and there's gain in here and blah, 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 blah. Anyway, here's its usable range. It looks pretty linear between about minus 50 and 0 dBm. So we will try that out. We will start at 0 dBm and go down and see if it stays linear. And this is at 5.8 gigahertz, so my equipment doesn't go that high. This chip is supposedly good from 1 megahertz to 8 gigahertz, so 70 dB dynamic range, so pretty amazing little chip. So if it does like the data sheet, I'm going to be quite pleased with this one. So we'll see what the different frequency responses in it too, the delta with frequency. Let's hook it up. I need to figure out what voltage to run this thing at. Input voltage. Single supply operation, 5 volts. So I guess we will hook up 5 volts. All right, so it's not working. I don't know why. I'm taking a look at the pinout and make sure this thing is wired up right. I'm suspicious that it's not wired correctly, so yeah, let me take a look at that. All right, I figured that was wrong. There's a 5-volt regulator on the board, so you need to input more than 5 volts. So if you input 7 volts or more, it seems to be working fine. So I just put in 12 volts because it's a low power device. So it's dropping the 12 volts down and making 5 volts, and now it's working just fine. So I did some measurements here. 0 to minus 60 dBm. Okay, so this is dB milliwatts. And I did it at 50 megahertz, 500 megahertz, and 1 gigahertz. And that's all the range I've got. Well, I can go lower, but I can't go more. Can't go above 1 gigahertz with this machine. So if you just took a look at 500 megahertz and 1 gigahertz, the numbers they're different, but they're not crazy different. This is voltage out of the device. So the voltage goes up as you decrease the input. So at 0 dBm, we're here at 0.932 volts. This is volts, and 0.910 volts. So a little bit of difference, but you know, it's certainly within what, 2%, 5%. Anyway, and then it does nothing from 0 to minus 5 dBm, minus 10 dBm. It's not doing anything, and minus 15 dBm. So it doesn't do anything down to minus 15 dBm, and then it starts working, and then it gives us increasing voltage from minus 15, minus 20, minus 25, all the way up to minus 60. So it is increasing, and the numbers are, like I said, within a couple percent of each other. So that looks like it's tracking pretty good. Now the story at 50 megahertz is different though. The story at 50 megahertz is they're quite a bit different. At the higher end, they're the same. So 0.1, 0.07, 0.9, but then it drops here. So I say, if we draw a line maybe here and here, I think it's working in that range, working quite well. I'd be pretty happy with that. So from minus 20 dBm to minus 55 dBm, anywhere from 50 megahertz to 1 gigahertz, it seems to be basically given the same number. So these are quite encouraging. So we need to convert that number into dBms and see how it tracks. So maybe I'll put these in a spreadsheet and kind of massage that. Now there is one oddity though in the data sheet. So I don't know if you can read that or not. So in the data sheet, this says it's a basic connection, okay? Basic connection. So we have the input coming through a 52.3 ohm resistor, and then after you get done with the loading of the machine, it's 50 ohms. So they used a 51 ohm, so that's good, 51 ohms. Then here's the two input capacitors. So this matches our circuit. There is some kind of temperature input I don't think that's being used. There's an enable pin that's just tied high on the PC board, so the part is always enabled. And then there's some biasing and stuff. And then there's this output, and the output is also tied to VSET. So pins 6 and 7 are shorted together. And they aren't on the PC board, they're separate. So maybe I want to go short those out. I don't know what VSET does. Let's see if we can find a block diagram here, VSET. Yeah, here's VSET and here's Vout. So they sum together. So the current to voltage conversion, then in voltage to current version comes back and sums in again. So there's kind of this weird loop here. Why do you tie those together? E set summation. This is just floating now, so maybe it's better. Yeah, maybe I need to tie those together and things will get better. It's a 9-stage logarithmic amplifier, so it's 9 detectors. So, yeah, that is really cool. Yeah, here again, tying those together. Let's go down in the data. It's quite a lengthy data sheet. I haven't read it yet. I should read it. Yeah, here again, V set and V out are tied together. Yeah, let me tie them together and see if the numbers change. Well, I shorted those two pins 6 and 7 together and didn't seem to make any difference at all. So I guess you could just use the board as is. So it's just fine. It measured exactly all the same numbers again. I went over here and they're just all the same. So I did go into the office and type them into Excel. It was a lot like doing work. It doesn't feel good. Anyway, so what I did was I have 50 hertz, 500 hertz, and 1,000 hertz, 1,000 megahertz. I'm sorry, 50 megahertz, 500 megahertz, and 1,000 megahertz, otherwise known as 1 gigahertz. And these are the voltages that come out, and these are the dBm power levels. Okay, and then what I did was I did a quick calibration. So I say that you subtract that many volts, and then you apply an offset, and then you apply a gain. And if you do that, then minus 15 is minus 15. So this is my cal point. I caled right there. So those are perfect. And then everything else is relative to that. And then I caled this point here. So this is my offset cal, and this is my gain cal. And then you can see these numbers, and then these are the errors. And so we're within, we're within about definitely within 2, and probably within 1 dBm, which is really, really good over a very simple calibration, over 50 megahertz to a gigahertz. So I'm really, really pleased with this chip. It is a really, really nice chip. That other chip I had was garbage. Wow. This chip is really, really nice. So I think this warrants actually building a box. So it's definitely going to be put on my list of things to do. I have these project boxes that I've been building different things into. I have a power supply, and I have a where did it go? I must have moved it. I have a synthesis chip, a frequency synthesis chip. And I think having a power meter would be a really good project for that box. So I'm definitely going to throw it in there and show you how to build it, because I think this power supply is actually going to be very, very valuable for a lot of people. People have commented on my power supply, on my, did I say power supply? Power meter. Have been commented on my power meter. They're way too expensive. To buy a power meter is way too expensive. And to buy a cheap power meter is way too crude. You can't just get a watt meter and say, okay, now I have a power meter. No. You need something that can measure down to these levels, because if you want to protect something like a nano or a tiny SA or nano VNA or stuff, you need to make sure you're below a 0 dBm, right? And something like this will be really, really valuable to know where you are, right? If you want to set your levels to around maybe minus 20 dBm before you start doing your measurements, or like I said, the tiny SA seems to work really, really well when you're down below minus 30, right? So yeah, this would be really good. And then if you need to measure higher power, well, then you put in an attenuator. So this is a 30 dB attenuator. So if this thing operates well to minus 15, and then you have a 30 dB attenuator, then you can measure up to plus 15, right? So, and then if you need more than that, you put it in another attenuator, and you just to keep attenuating it down, right? So these little attenuators are just dirt cheap. These little these little guys here, right? You can get those for not much money at all. So if you have first of all, you're going to need one that you're going to have to spend some money on. So you need one that can handle the wattage, right? This is good to 30 watts. And then once you get it down, it's going to get that 30 watts down to about a watt. And then you can use one of these and put that on the end, and then these are good for 2 watts. And then that'll get you down to the ranges where you can use your power meter. And like I said before, even the expensive power meters, you know, they don't like any more power than about maybe plus 10 dBm, maybe. And so even expensive power meters, you have to have attenuators in front of them if you want to do any work. So this would be really good. It seems to actually be pretty linear. So here's the plot of this data. This is 50, 500, and 1,000 megahertz. And you can see that it's very, very linear between minus 15 and minus 60. In fact, maybe I can even go to minus 65. It seems like it's getting up around the limit to it, though, right around here. I think it's going to do exactly this. I think it's going to flat spot here. But I haven't actually tried that yet. But I doubt that you want to be measuring power below minus 60, but certainly in the ranges of 0 to minus 30 dBm, that's like a real sweet spot for making power measurements. And so if you have a little attenuator, then you can basically then push this curve up, right? So if you put it in a 15 dB pad, then you'd be good from 0 down to minus 45, minus 50. So yeah, I think it'll be a really, really good project. So this is the Analog Devices 83, I wrote it down, didn't I? 8318, the 8318 chip. Really, really pleased with it. And I'll put a link in the comments below on what was the price of that thing. It's not much money at all. And this is how you get it. It has an SMA connector on it, and you just have to apply power. It has a 5-volt regulator, so like I said, you need at least 7 volts coming into this thing. And I was running it at 12 volts, and the regulator wasn't getting very hot. It was just a little bit warm. That's dropping a lot of voltage, but I don't think it takes much current at all. And so you put on power here, and then you get a voltage out. And that's all there is to it. Nothing on the back. Nice stitching of vias. So the RF layout of this thing is quite nice. So whoever built this board, you know, hats off. And Analog Devices, way to go. A really, really good power chip.